This problem is the cylindrical form of quick flow. In quick flow, we had two flat plates. One of the flat plates was stationary, the other one was moving at velocity v. Here, instead of having two flat plates, we have two cylinders. The outer cylinder is fixed, it doesn't move. The inner cylinder is rotating at a constant rotational velocity, omega I, and this I stands for the inner. So, we are after the velocity profile of the flow, which is created because of the rotational motion of the inner cylinder. Obviously, because we are dealing with the cylindrical geometry, we need to use the cylindrical form of Navier-Stokes equations or the cylindrical form of the continuity equation. But again, like always, the first thing that we have to do is that we have to read the problem statement carefully, and we have to understand the meaning of the words given there. So that's the first thing that I'm going to do before getting into the cylindrical form of continuity equation and then the cylindrical form of Navier-Stokes equation. Remember, both of these equations, the cylindrical form of continuity equation and Navier-Stokes equations in cylindrical coordinate, are given in Appendix D of the book, which is page 822. Okay, let's read the problem. It says, consider incompressible flow. So flow is incompressible, and you know the meaning of incompressible. That means rho, or density, is constant. So that's the first thing that we know. So it says, consider incompressible flow of constant density and viscosity between two eccentric cylinders. The cylinders are long, so that there is no axial flow. So it says there is no axial flow. When we don't have any axial flow, that means velocity in z direction is 0. And again, remember, we are in cylindrical coordinates, so we have z direction, we have r direction, and we have theta direction. Z is the axial direction. So it says there is no axial flow, so that means v in z direction is 0. And there is no end effect. And the problem statement is actually clarifying what that means. When it says there's no end effect, it means, because they are long, that means we don't have any variation in z direction. So that's the meaning of there is no end effect. So you see the first derivative of whatever fluid property or flow property you have there with respect to z is 0. It says the inner cylinder circulates at an angular velocity of omega I, while the outer cylinder is fixed. The velocity does not vary with theta. So that means we don't have any variation with respect to theta. So the first derivative with respect to theta is 0 and only varies with r. So velocity varies with r, meaning that the variation with respect to r is not 0. So you see, the variation with respect to z is 0. It's given here. Because there is no end effect, the problem says the velocity does not vary with theta, so the first derivative with respect to theta is 0. And then it says it only varies with r, meaning that the first derivative with respect to r is not 0. And then we need to analyze this flow, which means we need to find the velocity profile here. So I'm going to label these things, and then I can call them when I'm simplifying the Navier-Stokes equation in cylindrical coordinate. And then I will probably add a few more assumptions here. So like, I'm going to assume that this flow is steady. So this is number 1. That's the first piece of information that we have. And then this thing here is number 2, no velocity in z direction. This thing here is obviously number 3, meaning that there is no change in z direction. This thing is number 4, there is no change in theta direction. And number 5 is that we do have change in r direction. And then let's add number 6 and say flow is steady. Okay. And I think now we're ready to start with continuity equation. So I'm going to write down the continuity equation in cylindrical coordinate. And again, you can find this on page 822. So it's like 1 over r, the first derivative with respect to r, br. So that's the first term. The second term is 1 over r, the first derivative with respect to theta, and then v theta. and then the first derivative with respect to z, Vz, and then the first derivative of density with respect to time equal to 0. So this is continuity equation in cylindrical coordinate. So now we need to simplify this. So obviously this one is 0. Why? Because if we go back, we said number 1, the first piece of information, rho is constant, density is constant, so density does not change with time. So this is based on number 1. You need to see number 1 to understand this. Then the other thing which is 0 is this term, because if we go back, number 2 is that Vz is 0 because the problem says there is no axial flow. So C number 2. And then the other thing, if we go back, is that variation with respect to theta is 0. It says the velocity does not vary with theta. So the first derivative with respect to theta is 0. Here is the first derivative with respect to theta, which is 0. So C number 4. So this term is the only term that is left. So let's okay. So let's write that down again. It's like 1 over r. The first derivative with respect to r, rvr is 0, right? So then obviously this 1 over r cannot be 0, right? Because it's 1 over r. Cannot be 0. Then obviously the first derivative with respect to r, rvr is 0, and that means that this r, vr is a constant, and that's why its first derivative with respect to r is 0. So this is a constant, okay? Now, to find out what that constant is, we can assume that r is equal to r out, meaning that we are at the surface of the outer cylinder, and then we know that when we are at the surface of the outer cylinder, then that means velocity is 0 because the outer cylinder is stationary. So VR is 0. So that means, and we know that RVR is always constant. So R0 multiplied by velocity, then R is equal to R0, which is 0, is actually equal to that constant. So that means that constant value is 0. So RVR, which was equal to a constant, we just found out that the constant value is 0. So RVR is 0. And obviously that means that VR is 0. So we knew that, we already knew that we don't have VZ because the problem says there is no axial flow. And then we know that VZ is 0. And now we found out that VR is also 0. So I say, from the second piece of information given in the problem statement, Vz is 0. And now we learn that and actually I can say in from, because this conclusion was made from continuity equation, so I say from continuity equation, VR is 0, then the only non-zero component of velocity is v theta. Know what, this is important because the problem says find the velocity profile, and now we know that the velocity profile, which has three components, it has vr, vz, and v theta. We know that vz and vr are zero. As I say here, vz equal to 0 was given in the problem statement. That was kind of initial information. And then when we worked on the continuity equation, then we realized that vr is also 0. So when we are after velocity profile, we are actually just after v theta. So that tells me that the next step of my solution should be writing the Navier-Stokes equation in cylindrical coordinate in theta direction. So I'm going to write down the theta component of Navier-Stokes equation in the next slide and work on it, simplify it using the initial information that we have to find out the velocity profile, which is actually this v theta. So here's the Navier-Stokes equation in cylindrical coordinate in theta direction. As I said, you can find this in Appendix D of the book, which is on page 822. So I'm going to start simplifying this equation using the information given in the problem statement. So the first thing is that we don't have, we don't have gravity in theta direction, obviously. Gravity is just in z direction, it's downward. So that's 0. And then the second term is also 0. Gradient of pressure with respect to theta. Let's see why. Look at number 4. The first derivative with respect to theta is always 0. It says velocity does not vary with theta. So we don't have variation in theta direction, meaning that we also don't have a pressure gradient in theta direction. So you can say that that term is also 0. So then this term is not 0 because we do have v theta. And if we go back here, remember, this is what we found by solving the continuity equation. We have v theta. And then we also have variation with respect to r, because if you look at number 5, it says the first derivative with respect to r is not 0. So then the first derivative with respect to r is not 0. Velocity in theta direction is not 0. So the first derivative of velocity in theta direction with respect to r is not 0. And that's why I have to leave this term. And then when we go to the next one, this is 0 because of number, if we go back again, because of number 4, because when the first derivative with respect to theta is 0, obviously the second derivative with respect to theta is also 0. So this is because of number 4, and this is because of number 4. Okay? Then, a variation with respect to z. So if we go back, then it says there's no end effect. The meaning is that variation with respect to z is 0. Number 3, so when the first derivative with respect to z is 0, obviously the second derivative with respect to z is also 0. So this term is also 0 because of number 3. Then I leave this term because we have v theta, and I leave it. And then we don't have vr, so obviously this term is 0 because vr is 0, right? And if I go back, and that's something that we found here by solving continuity equation, that VR is 0. So I can say this is 0 because VR is 0. And we found this through continuity equation. So I assume that the flow is steady, so we don't have any variation with time because flow is steady. And if we go back, I said, so this is number 6 actually. Then we say flow is steady. And then so this is 0 because of number 6. And then here this term is 0 because VR is 0, similar to the other term here, right? And then here v theta with respect to theta, this is 0, and this is number 4 again. If we go back and look, number 4. And then we have vz multiplied by the first derivative of v theta with respect to z. This term is also 0. We don't have vz. So if I go back, this is, I think, number 2, yeah? there is no axial flow, so Vz is 0. So this is because of number 2. And then here we have Vr, which is 0. And again, we found this using continuity equation on the previous slide. So we are left with just 2 terms. So the remaining terms are 1 over r, the first derivative with respect to r, the first derivative of theta with respect to r, right? Plus, minus actually v theta over r squared equal to 0. So we have to solve this, okay? So I can write this as, I can simplify this and write it as this. So it's like the first derivative with respect to r, it's like what I'm doing here is this. I'm multiplying this equation by 1r, and then this is gone, and then this thing here is also gone, right? So it's like just the first derivative of that r, the first derivative of v theta with respect to r, minus, minus v theta over r equal to 0. So this is what we have, right? And we want to solve this equation. So I can take this, I can simplify this term and then write it as, so it's like the first derivative of the first term multiplied by the second term is going to give me the first derivative of r with respect to r multiplied by the first derivative of v theta with respect to r plus the first derivative of the second term, which is multiplied by the first term. So it's first term over r. So we can simplify that as this, and obviously this term here is 1, right? So we are left by these 3 terms then. We have r, the second derivative of v theta with respect to r, plus the first derivative of v theta with respect to r, minus v theta over r. Equal to 0. Okay, so if we multiply both sides by 1r, then this is what we get. Then we get r squared, the second derivative of v theta with respect to r, plus r, the first derivative of v theta with respect to r, minus v theta equal to 0. So this is an ordinary differential equation, and we need to solve this. So I assume that the first derivative of, so let me write the solution in, let's say, a different color. So I say, let's say the first derivative of v theta with respect to r, let's call this v prime theta. And then the second derivative of v theta with respect to r, let's call this v second, v double prime theta. Okay. So if I do that, then I can say this equation, therefore this equation that we have here is like r squared v double prime theta plus r v prime theta minus v theta is equal to 0. So this is the equation that we need to solve. And you know how to solve this from differential equations. Okay, I'm going to write the solution here for you, but this is not fluid mechanics, and you know this. It's just a kind of quick review of how to solve that differential equation. So to solve that, you assume that v theta is r to the power of m, right? And then if that's the case, then you substitute this into that equation, and then you solve it, and then you find M1 and M2, and then you say the solution, which is V theta, and is actually what we are after. We're after this V theta, right? So the solution V theta is like C1 R M1 plus C2 R M2. And C1 and C2 are integral constants, and you can find them using boundary conditions, okay? But you have to substitute that V theta with R to the power of M, and then you will get a second degree equation, and then you solve that equation, and then you find M1 and M2, and then here's your solution. So if we do that, if V theta is R to the power of M, then V prime theta is like M R to the power of M minus 1, and then V double prime theta is like M times M minus 1, and then R to the power of M minus 2, okay? So we substitute these into that equation, that differential equation that we have here, okay? So it's like R squared times V double prime theta, right? So I would say I have R squared V double prime theta plus R V prime theta minus V theta equal to 0. So this is the equation that you're solving, right? So instead of this, I'm going to have this term goes here, okay? And then instead of this one, which is V prime theta, I'm going to have this term going there, okay? So I'm going to say I have R squared, okay? I have R squared times, then I have M, and then M minus 1, and then R to the power of M minus 2, plus we have R times V prime, which is M R M minus 1. And then we have minus this V theta, and V theta is R to the M. So minus R to the power of M equal to 0. Okay, so now we can simplify that as we have M, and then M minus 1, and then R to the power of M, right? And then we also have M, R to the power of M, minus R to the power of M equal to 0. Therefore, we can take that R to the power of M out. So it's like R to the power of M, and then we have M minus 1 plus M minus 1 equal to 0, okay? So if that's 0, the first term cannot be 0, so the second term is 0. So then I would say M times M minus 1 plus M minus 1 is 0. Then this is like M minus 1 times M plus 1 equal to 0. Therefore, M1 is like 1, and M2 is like minus 1, okay? And then from here you can say V theta, which is velocity, and this is what we are after, is C1 R plus C2 R to the power of minus 1. And now you need to use the boundary conditions to find C1 and C2. So this is, some have most of the solution. So the last part is just using the boundary conditions to find C1 and C2. So I'll write the boundary conditions, and I'll write the final form of this equation. But I leave finding C1 and C2 to you. So the boundary conditions that we have are these. So obviously, at R equal to, let's go back to the figure. So when we are at the surface of this one, this cylinder, So the velocity is equal to the velocity of this cylinder. And then when we get to the surface of this one, velocity is equal to the velocity of that one, which is 0, because that one is a fixed and this one is rotating. It's like finding boundary conditions for flow between two flat plates. One of them was stationary, so velocity was 0 at y equal to 0. And then at y equal to h, when we were at the upper plate and the upper plate was moving at the velocity of v, then we would say that velocity of the flow is equal to v. So it's the same thing here. The inner cylinder is stationary, so we say velocity at the surface of the inner cylinder is equal. The inner cylinder actually is rotating here, so we say velocity of the flow at the surface of this inner cylinder is equal to the rotational velocity of this cylinder, and then the same thing for the outer one. So I write one boundary condition when r equals to ri, and one boundary condition when r equals to ro. So it's going to be like this. So when r is equal to ri, then we are at the surface of the inner cylinder, then we would say v theta is equal to ri omega I. R omega is velocity, right? So that's the first boundary condition. This is basically boundary condition 1. And then when r equals to ro, we are at the surface of the outer cylinder, which is stationary, then v theta is equal to 0, and this is basically boundary condition 2. So if you use these two boundary conditions to find C1 and C2, then you will see that the final form of v theta is like this. And you need to do a little bit of simplification, and then you have omega I, ri, and then we have r0 over r minus r over ro, sorry, and then we have ro over ri minus ri over ro. Okay, so this is constant, this rho omega I is constant, ri is constant, r out is outer radius, ro is constant. So this ro is constant, ro and ri, both of them are constant. So the only variable here on the right side of this equation is actually r. So this is the only variable, and this r here, these are the only variables, and then this v theta is the only variable. So you see, actually you found, what you found here is v theta as a function of r, and you can plot it. If I give you values for ri, for ro, for omega I, then you can simply plot, you can find that function, which is like this. You just need to substitute the values in there, and then you can plot this theta, this v theta velocity in theta direction as a function of r. So it is a pretty long problem, but it's not difficult. It's actually, you just need to have a good understanding of the information given in the problem, and then you have to understand that you need to use the Navier-Stokes equations in the cylindrical coordinate, and then use the information given in the problem statement to simplify that equation, and then you need to know how to solve the final differential equation, which I quickly reviewed here for you. Okay, so yeah.